Hello and welcome. PC model is probably the most important model in thermodynamics. It handles fluids, phase change fluid, that is, fluid is allowed to change its phase from vapor to liquid or liquid to vapor. So in this extended video, we are going to cover a number of state evaluation involving PC model. We'll use the system state TESTapp, and we'll begin with a simple problem and progressively make the problem a little more complex. In every problem we solve, we'll solve the problem manually as well as verifying the solution using the TESTapp. So any problem property evaluation begins with a TS diagram, a thermodynamic plot, because you got to make sure you know how to find where the state belongs. So in this problem, the pressure is given 200 kPa, so we assume this is a 200 kPa line, so the solution must be somewhere along this line. And also it's given a saturated liquid, so that gives away the state very easily. This is the liquid line, so the F point must be our state 1. So for state 1, we are supposed to find what is given, pressure is given, and saturated liquid means X equals 0. We are supposed to find enthalpy. So let's go. So let's go and open the property tables module of test. And as you can see, the PC model is right here. All these tables are here. And we can launch the TESTapp right by clicking in this cell. So we are after enthalpy at a given pressure, saturated liquid. So therefore, we open the saturation pressure table. And at 200 kPa, it's a relatively simple problem. At 200 kPa, as you can see, the enthalpy of fluid, the liquid, saturated liquid is right here, 504.7. So we pick up this number and write our manual solution, 500, I believe it was 504.7 kilojoule per kg. And now let's go and verify the solution. To do so, we launch the TESTapp. Conveniently, it appears on the side on the other side. So pressure is given, 200 kPa. So you can go back and forth once we have the solution between the TESTapp and the manual tables. Notice the enthalpy has been found, 504.7, almost the same. And nice thing about here, we can go to the graphics panel and make sure we didn't make a mistake. Look, the solution is, as you can see, it is a saturated liquid state. That's why it's on the F line. If it was somewhere else, immediately visually you could realize that we made a mistake. So let's move on. Let's solve another problem. So we have just verified this solution, so we can write that this solution has been verified. And that's what we are going to do for every problem. Okay, so in this problem, the pressure is given to us. So again, we draw a constant pressure line, which is 520 kPa. And quality is given as 30%. So our state must be somewhere between the F and G state. Let's say this is our state, which is state 2. And we are asked to find entropy. We know entropy is going to be 1 minus the quality, which is supplied to us, and then saturated value at liquid at the given pressure for the entropy, and X times SF at given P. In other words, it's a weighted average of entropy for the saturated liquid and saturated vapor. Oh, this is not F, I'm sorry, as G at P. So we have to go to the saturation table, pressure saturation table, because pressure is supplied, and pick up these two numbers. And X is given, so it's a fairly straightforward problem. So if we set it up, it's 1 minus 0.3 times whatever value we get from the table, plus 0.3 times whatever value we get from the table for that. So we go get started. Again, we'll go to the property tables, saturation temperature, saturation pressure table, I'm sorry, 520 kPa is 0.52, so it is somewhere between, if you notice, 520 will be between somewhere between 50 and 55, 0.5 and 0.55. These are MPAs. So if we go, so we are supposed to pick up both the SF and SG. The last two columns you can verify are this is the SF column here, F column, and this is the G column for entropy. So it'll be somewhere between these two numbers, 1.86 and 1.89. Let's say we'll pick up 1.87, and here let's say we'll go somewhere in between, let's say 6.81, and just with this eyeballing estimation, we'll find out the values. So, and then we'll compare that with the exact test results. So this is what we are 6.81. And I have already done this calculation. If you do that, you should find it to be 3.35 kilojoule kgk. Going back to verify, all we do is to launch the TESTapp and enter the known quantities, which are 520 kPa and X is 0.3 or 30%. And we do a calculate. That finds entropy for us, which is 3.353, very close to what we got. And go to the graphics panel just to verify visually that we didn't make a big mistake. The state is definitely in between F and G states. So therefore, we have solved this problem. Let's proceed to the next one. In this problem, the quality is not supplied. So it's a little more difficult problem, more typical. Instead, entropy is supplied. The pressure is known, again, the same pressure, 520 kPa. And we are given entropy, but we don't know where we belong. Is it a subcooled liquid, a mixture, or a superheated vapor? We have no clue right now. So the proper way to go is to figure out what are the entropy at the F and G state, and then compare the given entropy with those values. We've done that already in the previous problem. SF at 520 kPa in the last problem we solved. We went to the table and got these numbers. I'll just not write the unit. There's no point because it'll be repetitive. So S values at F and G point we found were these. And look at the given value. The given value is somewhere in between. Therefore, we must have a mixture. If the given value was more than 6.81, it will be a superheated vapor. If the given value was less than 1.87, then definitely we'll have a subcooled liquid. But given the situation, we must have a mixture. Now that we know the mixture, we know that S of the mixture is always given by this formula. SF is a weighted average by the quality. How much liquid, how much saturated liquid is there? X being the percent or fraction of saturated vapor. So this is, if X equals 0.5, you can see it will reduce to a simple average. So now here we know S is given 3.352. Quality is the one we are after. SF is 1.87. So there is only one equation and one unknown. Solving, you can show that X become equal 0.3 again, because that's the problem we began with really. So now that we know the quality, we can go and find out enthalpy, because what is enthalpy after all? Enthalpy of a mixture is also the same way, just like entropy is given, HF at the given P plus X times Hg at the given P. So all we have to do now, 1 minus 0.3, go to the table, find this value, 0.3, find that value, and we got our enthalpy. So we go to the property tables, again, pressure table, And at 520 kPa, which is given to us, which is between these two, the enthalpies are HF and Hg, you notice, are this table. So therefore, we have this pressure in between the two 520 kPa. So we can eyeball enthalpy. This is our HF. HF could be somewhere in between. Let's say we'll say it's something like 650. And this also will be something in between. Hg 2753 and 2748. Let's say 2750. So we'll carry these numbers into our solution, and putting the numbers together, it's 0.7 times 650 plus 0.3 times 2750, and that gives us an enthalpy of 1280 kilojoule per kg. All right, so let's go and see if we can verify this solution. How? We go back here, launch the TESTapp, and notice how easy it is, because the procedure for the TESTapp remains the same. We know the pressure and we know the entropy. We don't have to go through all the reasoning anymore, which is 3.35, right? That was given to us. And if we just calculate, it finds the enthalpy for us, which is 1275, which is pretty close to what we found. Again, the graphics panel will show that we do have the solution inside the dome. That means it's a mixture. So the problem, so that we have answered the question, and the answer has been well verified. 1275 as opposed to 1280. Percent-wise, the difference is almost nothing. Okay, in this problem, notice that the temperature is supplied. Pressure and temperature both are supplied, and we have no clue again where the state belongs. Of course, we start with our constant pressure line as usual, because the pressure is given to us. So the state will be somewhere on this line. Now, to get an idea where the temperature 425 is, we should not just assume the steam to be superheated or a mixture. We have to prove it to ourselves. So notice that we have a good handle on this temperature. What is this temperature? This must be TSAT at 520 kPa, which is, we can go to the table, and if you open the pressure saturation table, 520 kPa, we've been going to the same place over and over. So at 520 kPa, we can eyeball the saturation temperature, the boiling temperature, which is about 151, 155, I'll say 153 degrees Celsius. So notice how this helps, because now that we know that this temperature is 153 degrees Celsius, we can easily estimate that for T equals 425, that line would be somewhere above there. So let's say, just we arbitrarily assume this is our 425 line. This temperature is 425. Doesn't matter, anywhere above 153 line, that means our solution must be somewhere along this line that satisfies the temperature requirement, and along this pressure line that satisfies the requirement of the pressure. So the only thing is that the final state, state 4, must be somewhere on the superheated side of the dome. Because if you notice, even if you say, okay, my 425 is really here, even then you will end up with a state that is on this branch. That is a superheated vapor branch of this face dome. So the problem becomes considerably simplified. We go to find the enthalpy, we must go to the superheated table and look for, so instead of the pressure table, we go for the superheated table of H2O and look for 520 kPa. Notice the pressure is given on the top for each table. The superheated tables are separated by pressure, and 0.52, there is no, unfortunately there is no pressure 0.52, so we know we have to interpolate between these two tables, becomes a little bit hairy. And the temperature is given to us. Temperature given is 425. 425 falls down somewhere between these two, in fact smack in the middle of these two. And we know to find enthalpy should be either between these two for this pressure or these two for that pressure, for 0.5. So our answer will be somewhere between these four numbers, and that really requires a bilinear interpolation that can take some time. So the middle of these two number, whatever that is, and middle of these two number, whatever that is, and then not exactly middle because we are trying to find 0.52 and something closer to this side. That's what we need. So if we have to estimate, I'll say, if I pick a number, let's say 3330, just out of, blue. It cannot be that bad. Even if you pick any number between those four, among those four, in between, you cannot go wrong. You'll be very close to the correct answer. But you can gradually improve your estimate once you solve a number of problems. Okay, so let's go and see if we can reproduce that solution, what we get from the TESTapp. Again, the pressure is given to us as 520 degrees Celsius, 520 kPa. And the temperature is how much? 425 degrees Celsius. We calculate the state. Notice that the superheated vapor, the phase condition is produced like as we expected from our theory, and the enthalpy produced is 3324. We kind of lucked out. So we got a enthalpy of 3330 was my guess, and 3324 is from computer, from test, which is way more accurate. So think of the percent difference between what we got manually and what we got by computer. So once you get good at it, you should not spend a whole lot of time interpolating properties. You should be just picking it up from the table by guessing, intelligently guessing, and then using the TESTapp, verifying, and you will see that you save a lot of time solving any thermodynamic problem. Well, once again, in this problem, you can see that we know enthalpy and pressure, but we don't know where the state belong. Just like we did in the last problem. Pressure is given, so this is our 520 kPa line. We know the state will be somewhere on this line, but to figure out the composition of the state, we go after the HF, the saturation liquid enthalpy at 520 kPa, and Hg at 520 kPa. Again, we have been doing that a number of times, so just to show you how we do that, go to the property tables, which is already there. If you go to the pressure saturation table at 520 kPa, which is between these two numbers, the enthalpies are these columns. So we are between these two guys, and the enthalpies are somewhere here will be HF, somewhere between those two will be Hg. So let's say we'll eyeball it to be 650, and let's eyeball that to be 2750. So with these numbers, if we go and write them down here, we can very easily estimate where our state is. Our state is an enthalpy of 3324. Notice for F and G, we now know the values of enthalpy, and the given value is way higher than Hg. So therefore my state might be somewhere superheated because it's on the right side of G. So let's call it state 5, which is a superheated vapor. And now we know the enthalpy of the superheated vapor and the pressure. So therefore it's a simple problem. Now the pressure is given, P5 is 520 kPa, and enthalpy is known, 3324. And so therefore we can go to the superheated table and figure out what specific volume is. That's what is wanted in this problem. If we go back and this time again we launch the superheated table, and we go to, so we search for 520 kPa superheated table for that, which is between these two tables, and look for an enthalpy of 3324. So it'll be somewhere, 3324 will be somewhere between these two guys here and these two guys there. So as you can see, the specific volume therefore will be somewhere, has to be interpolated between these numbers and these numbers. So if we eyeball it, it'll be somewhere between 0.61 and 0.71 here, and that's kind of like, let's say 0.65, and it's somewhere between 0.51 and 0.59, let's say 0.56. So just to get a ballpark number, I'll say maybe 0.63. Okay, that's a quick and dirty job, and let's quickly go and check what we get. So our guess is 0.63. And what we get if we do it using TESTapp, the exact correct solution, it's already open, so we can just go and calculate our state 5. Let's call it our state 5. And what we know is that enthalpy is given and pressure is given. Pressure is 520 kPa, and enthalpy is given as 3324. Do you calculate? The state comes out to be, the specific volume is done with 0.615, about 0.62, which is pretty close to 0.63 we estimated manually. Okay, here is another problem where we don't know the phase composition, only pressure and temperature are supplied. So we draw a constant pressure lines, which is 5000 kPa this time. So the state 6 must be somewhere on that line, but the temperature is not known. So to get an idea where the phase composition falls, let's find the saturation temperature, TSat, at 5000 kPa. In other words, at what temperature water will be boiling at 5000 kPa. So we go to the pressure saturation table, find out 5000 kPa, which is 5 million pascal. And for 5 million pascal, as you can see, the temperature is 263.99, which is 264, pretty much. So if the temperature is 264 degrees Celsius here, we know our state has only 25 degrees Celsius H2O. So if we do a 25 degrees Celsius, which will be way below that, let's say it's somewhere here, then obviously the state is going to be right here, and it's a subcooled liquid. So we figured that out by reasoning that it's a subcooled liquid, and we have to find entropy and enthalpy. For finding properties of subcooled liquid, you use something called a CL submodel, the compressed liquid submodel. According to that submodel, V of this liquid is given by Vf at T. This is a function of temperature only. Similarly, U is given by that, and entropy is also given by Sf at T. In other words, V, U, and S, according to these submodels, are function of temperature only. So if we know the temperature at 25 degrees Celsius, all the properties along this line, V, U, and S, do not change. So we can go to the F point and pick up the property that we desire. So then what will be S? S will be Sf at 25 degrees Celsius in this case, which is, we can go back to 25 degrees Celsius means it will be better to open up the saturation table, temperature saturation table, and we can go to 25 degrees Celsius and pick up the entropy, Sf, which is, as you can see, 0.3674. So 0.367 will be our answer, approximately. So we found the entropy at state 6. To find enthalpy, recall that enthalpy is by definition U plus PV, and we know how to find U of a liquid by at the temperature given P and V. So notice U and V are function of temperature alone, but enthalpy now depends on pressure. So therefore at 25 degrees Celsius, if we find U, at 25 degrees Celsius, if we find U, which is, as you can see, UF is 104.88. So we put that value there. Pressure is 5000 kPa, and VF will be, I'm pretty sure, 0.001, 25 degrees Celsius, but you can go and verify. 25 degrees Celsius is pretty close to 0.001. So therefore, the enthalpy is found to be about 104.88 plus the pressure effect, 109.88 kilojoule per kg. To verify these answers, we go back, follow the same same test step, and we know the temperature is given to be 25 degrees Celsius and pressure is given to be 5000 kPa, and we found entropy to be exactly what we found by manually, and you can see the enthalpy is also very close to what we just got. Okay, so this is our final problem in this series. We have to find the change in enthalpy and entropy of liquid water. Well, of course, it's not given it's liquid, but as the water is pressurized from 100 kPa to 5000 kPa. So we start by drawing constant pressure line at 100 kPa and let's say 5000 kPa. We know already at 5000 kPa, the water boils at a very high temperature, which we can get by going to 5000 kPa, which is 151 degree Celsius. 5000 kPa means 5 MPa, 264 degrees Celsius. And at 100 kPa, this is a common knowledge. We know that the water boils at about 100 degrees Celsius. I mean, we can go to the table and verify, but we kind of know that. Under atmospheric pressure, water boils at 100 degrees Celsius. But our given states are given state, let's call them state 1 and 2. So 25 degree will be way over here. So maybe this is our state 1. Oops. Well, window could not recover, so I had to restart the solution manually. So let's go finish it off. At 25 degrees Celsius, let's say this is our 25 degrees Celsius line, then this will be our state 1 and 2 respectively. This will be our 1, this is our state 2. And we are supposed to find change in entropy and change in enthalpy. Notice that obviously both the states are in the subcooled region, and we can use the CL submodel, subcooled liquid model, for property evaluation of a liquid. And we know that S for a liquid is given by SF at the temperature given. So therefore S1 must be equals S2 because the temperatures are same. It's already given 25 degrees Celsius because S equals SF at 25 degrees Celsius. So the difference S2 minus S1 must be equal 0. So that's an important result. If temperature remains constant of a liquid, entropy remains constant, and vice versa. So in an isentropic pump, for instance, entropy remains constant, and therefore you can expect temperature to remain constant. And then evaluation of enthalpy becomes simplified because what is enthalpy by definition, which is a little tricky to find because it depends on pressure for a liquid, whereas U is a function of temperature alone, and specific volume also is a function of temperature alone, just like U and S. So therefore delta H, which is H2 minus H1, in this case, if you do the math, essentially this is a T2 plus P2 VF at T2 minus T1. And now we know these guys are equal and these guys are equal. So the expression simplifies VF at T1 or T2 times P2 minus P1. So in other words, which is 0.001, VF at 25 degrees Celsius will be very close to that. We can go and verify if you want. And then it's 5,000 minus 100, which is 4,900. So it will be 4.9 kilojoule per kg. We can go and verify quickly. We launch. The test tape is already there. Let's say super initialize. State 1 is given 100 kPa and 25 degrees Celsius. And state 2 is given 5,000 kPa and temperature didn't change. T2 equals T1. And in the I/O panel, we can go and find equal H2 minus H1, which is evaluated here 4.9 in SI units. It will be 4.9 kilojoule per kg, and that's exactly what we got. So the answer has been verified.